what? What's in the nucleus, right? So you're remembering what two particles are in the nucleus? Protons and neutrons. What about something like when you see positrons and neutroniums? What should you say when you get a question and it has an answer like that? Sounds really nerdy and smart. Always, if you see something like that, stop and go, I've never even seen that word before. If that's the case, don't pick that answer. Unless you didn't study it, then everything's open game, right? But if you've class and you've read through the study guide and you went to lab and you did the exam review and you're doing all those things, and here comes a brand new term you've never heard, it's probably something we made up. Don't pick it, okay? I'll be honest with you too, half the time, that's like a random made-up word. I don't even know what a neutronium is. I don't even know if it's a thing. Positrons are, we'll talk about them. But be hesitant. Sometimes students will go down that path, they'll be like, that sounds right, even though you've never heard it before in your life. Don't do that. Okay, trust yourself on these exams. Okay, here we go. Nice job. B, 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 B. Which of the following elements plays a critical role in water balance? Oh no, I made you learn the symbols. Give you a hint now that there's 2 seconds left. It's sodium's little buddy. Oh, shoot. What? Oh, no. It's terrible. Chloride. Chloride is a very important molecule. There's 3 of that, or actually 2 that play the biggest role, sodium and chloride. Okay, so this is good. I'm glad that we have, it's not good, let me back up. I'm glad that we highlighted a potential area where a little more studying needs to be done. Not hydrogen. Even though hydrogen is part of the water molecule, just the hydrogen guy itself isn't playing a role in water balance. So you got to think of water as H2O, like together. It can't be like hydrogens and oxygens. Hydrogen acts a certain way. Oxygen acts a certain way. Hydrogens, 2 of them and oxygen, becomes a new molecule that acts a certain way. Okay, so I think that may have been what happened. You're like, oh, I recognize that there's 2 H's and an O in water. But when we're talking about water moving in the body, it's attracted to things that we call solutes. And we'll talk about solutes in a minute. Sodium, chloride are 2 really important solutes. Okay, uh-oh, now I'm nervous for the next ones. Nice job, T the train. Here we go. You're iron, and someone just stole 2 of your electrons. What you look like now? So much griping. Jeez. This question's too hard. So I'm getting the vibe you don't love chemistry quite yet, right? Okay, so another test-taking tip. Which one could you probably throw out? This guy, right? He kind of looks a little different than the others. And so sometimes you can say like, okay, wait. I think I'm getting the idea that iron's chemical symbol is what? Fe. But now what have you got to decide? How many positive charges it's going to have. So if I've robbed 2 electrons, what would we expect the charge of this guy to be? Positive 2, right? Remember our balance between protons and electrons? So if I take away 2 of those negatively charged electrons, I would be left being positively charged plus 2. So in remembering the symbol is Fe, that would leave this guy being correct, not this one. So how it starts with, that's a good question. We always assume, unless we've given you other information, that if we're starting with an element and doing something to it, we're starting with it being neutral. Nothing is really abnormal or out of balance. So we'd say same number of protons, same number of neutrons, same number of electrons. Yeah. So if I started, the reason that these other ones were wrong, if I started with a balance of protons and electrons and took away 2 electrons, now I'm going to be positively 2 charged. If I had taken away just one electron, then I'd expect one charge. Or if I took 3 electrons away, I'd be plus 3. Okay, and we'll go back into that. We'll talk a little bit more about that today, too. We'll review that. Okay, let's go into our next huge embarrassing failure, shall we? Nice job, Lionhead. I'm more nervous about this one than the water balance one. So I'm going to imply we maybe didn't spend as much time studying over the last couple days as we maybe could have. So nitrogen is an important molecule or important element in proteins. In fact, when we look at the way the body processes nitrogen, in the blood we get something called blood urea nitrogen, BUN. It's an important thing that we can measure. It's also something that we see coming from protein breakdown. So there's a list. It's got 4 great elements or 4 elements that are critical in the body. And then the next slide has like 10 of them. We call them lesser elements in the body. That's where I'm pulling this from. This is not magic. So maybe go back, get that star in your course packet, highlight it. Say, Travis is going to beat us up next time. All right, let's do some more of this stuff. Arrgh! Pirates don't get enough of this, so their teeth fall out and their blood doesn't clot. They get scurvy. Pirates. It rhymes with schmalcium. Yay! All right, I don't hate you anymore. Good. Calcium, right? You can't have fresh fruit out at sea for like 3 weeks, right? It rots and goes away. How are you supposed to get that calcium now without fruits and vegetables? Right? So think pirates. Or not. All right, cool. Nice job, Lionhead, again. Okay, oxygen has 8 protons and 8 electrons. If I removed a proton, what would you change? Or what would change? This one's a hard one. Okay, good. All right, we're back to like most people getting it right. So I'm going to argue, though, don't protons weigh something? They weigh 1. So wouldn't I be changing the weight of oxygen if I took a proton out? Someone argue with me. Would I be changing the weight of oxygen if I removed a proton? How many people think yes? That's okay. How many people think no? I'm going to side with the no's. Why am I not changing the weight of oxygen if I remove a proton? Because it's not oxygen if I remove a proton. Because oxygen has 8 protons. If I yank one of those out, I now have nitrogen, not oxygen. Okay? So remember, it's the number of protons. Oxygen can't have 7 protons. That's what nitrogen has. Okay? So you got to be careful about that. You could say the same thing about the charge. Well, protons are positively charged. If I remove one from oxygen, wouldn't I have like a negatively charged oxygen molecule? No, because I just turned it into nitrogen. There's no such thing as oxygen with 7 protons. Okay, so you're changing the element anytime you're changing protons. All right, here we go. This guy is neutrally charged, has 11 electrons. What is it, and how many protons does it have? This is a hard question, too. Hey, nice job. Very good. So it's not niobium, even though that is an element. The chemical symbol for niobium is Ni. And we've never talked about it, so it's probably not a good one to pick. You're like, niobium, what? But again, don't bite at that thing that sounds right, but you've never heard of it before. So sodium has 11 protons. How do you know it has 11 protons and not like 10 or 8 or whatever? Because it's neutral. So in order to be neutral with 11 electrons, you must have what? 11 protons to balance those. If and sorry, has 10 electrons and 11 protons. Sodium has 11 protons, but 11 protons, 10 electrons. It would have what kind of charge? Plus 1. Yes. We're always talking balance of protons and electrons if we're talking charge. Good. All right. Ooh, Lionhead, you're killing it. Last one. Oh no. Nitrogen plus neutron. What's going to happen? Redeem yourselves, everybody. Yay. It's pretty good. It will have less mass. Okay? Why will the charge not change? It doesn't have a charge. Look at the name neutron. It's neutral. Neutral means no charge. It's neither positive or negative. It's in the middle. So a neutron does not have a charge. So you can add as many as you want, take as many away. Charge isn't changing. Will I not have a new element? What changes the element? Protons. Good. And then the chemical properties come down to what? Number of electrons. Yeah, it's the number of electrons that they do the weight. Yeah, so that's the right answer. So neutrons contribute to the weight, but not the chemical properties. Not the name of the element or what the element is, nor the charge. So they're just weight. It'd be like if you had rocks in your backpack. Someone's like, why you got those rocks in your backpack? I just want to make it heavier. Okay, cool. Don't really do much for you. They're just adding to the weight. Okay, should we see who won? It would seem like it's Lionhead, but let's get the results. Oh, silent guy. I don't know if they just weren't as fast, but got them all right. So whoever this person is, thank you for studying over the last couple days. I kind of want to give you a hug. Because everybody else, just kidding. But for real, those are the types of questions that you might get. They probably won't be worded as dorky, but don't be surprised when those types of things show up on your upcoming exam. Okay, so hopefully you've all made a couple little notes. Like, I don't know what water balance is, or I didn't study my list of important elements in the body. Okay, I'll stop beating you up. But that was kind of fun. Kind of. All right, we had talked a little bit about the periodic table, yes? Talked about protons, electrons, neutrons. Okay, we okay to move on? Questions before we get rolling? Has your love for chemistry increased or decreased? Or stayed the same? All right. Okay, here we go. A lot of this stuff, you guys, I want you to look at it and be like, oh, that seems logical, or that makes sense. Please don't memorize these little facts. You will hate chemistry forever if you don't make it functional. Does that make sense? I'd much rather you be like, hey, the atomic number is that number I see on the periodic table, and it's telling me number of protons, which makes total sense because number of protons is what? What's it determine? What that element is, right? So that would be a smart thing to have right there on our periodic table. Okay, our mass number, where's mass coming from if I'm talking about an atom? Protons plus neutrons. So that's not hard. You're like, hey, mass number of this guy. If something had 3 protons and 3 neutrons, we could say it would weigh what? 6. This doesn't have to be like crazy hard. This should not be a question that you're sitting there, you're like, oh, geez, 3 protons plus 3 neutrons. Remember we said they just weigh 1. Okay, now what if this had 4 protons, 4 neutrons, and 4 electrons? Now what does it weigh? 8. Why didn't we count electrons? They don't weigh anything. A, they're super teeny tiny, and B, they just kind of fly off and do their own thing, and so we can't really add them to the mass of this thing that we're looking at, the atom. Okay, so the atomic mass, and we'll get into this a little bit more in a second, it would be the average mass of that thing that we find in nature. Okay, and I'll explain that in a moment. So, simple case in point, simplest element, hydrogen. If you look at this guy, in most situations, all hydrogen has is one proton, and it dumps that extra neutron. It doesn't even have a neutron with it. So when you look at its atomic number is 1. But if we look at its mass number, it's also 1. Because all I have is that one proton adding to the weight of this guy. Okay, so if you look at it, you've got that little electron flying around somewhere out here, and my proton. Easy. This is going to blow your mind, and I don't want it to. What is this if I write that down? It's still hydrogen, right? But it has a positive charge. I heard it over there. What is that guy? Someone said it, now they don't want to say it again. How would I get to this? How would I get a positively charged hydrogen? I have my proton, and the electron's gone. Good. That happens all the time, you guys. You will see us use this, we call it hydrogen ion. You'll see us write that all the time. Hey, I got hydrogen ions over here, blah, 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 blah. These guys are the ones that contribute to pH. But when you're looking at that, I want you to think, oh my, that's just a proton. Because it's hydrogen, had one proton, and one electron to start with. If I dump the electron, become positively charged, I'm really just a proton. All right. So here's what it looks like on our periodic table. You can grab any element here and get this information. So let's start with hydrogen, because we're talking about it. So if I look at hydrogen with its atomic number of 1, what can I say about it? It has 1 proton. And you'll notice none of these guys on our periodic table have like a plus or a minus. They're not charged. We'll talk about ions in a second. So if it's not charged, then it's going to have 1 proton and 1 electron. Great. Okay, now how many neutrons would this guy have? And this is kind of a hard question. We talked about it a second ago, but how many neutrons here? 0. How do you know that, besides the fact that we told you? Yeah, look how much it weighs. Just 1. Where's that 1 coming from? The proton. Now, here's a question for you. Why does it weigh 1.0079? So 1.008. So the idea is, and let's go ahead and just round this up, 1.01. That's a 1 in the hundredths place. That means out of every 100 hydrogens that we see in nature, 1 of them is going to have a neutron. And that 1 that has the neutron would weigh what? 2, because I got my proton that's adding 1 and my neutron that's adding another. So what we have to do is we have to take all of the naturally occurring hydrogens and we take their average weight. Okay? It would be like if I took all the students at Weber State and I made them all weigh themselves. And then I could get an average weight of students at Weber State. Okay, you may have some that are outliers, they're bigger or smaller, but I could get the average thing out there, the average student, what they weigh. Let's look at another one, boron. Okay, how many protons does boron have? 5. How did you get that? That's that atomic number. Is that ever going to change? Can I manipulate that? What if I added a proton? Do I have weird boron? No, I have what? Carbon. Okay. What if I added a proton carbon? Nitrogen. What if I add a proton of that? See, we're changing the element. So that's not something we're ever going to change. Okay, so I've got 5 protons. If it is neutrally charged, how many electrons? 5 electrons. Okay, and what about the neutrons? On average, I'm looking at how many? 6. Why? Where'd you get that? What's its atomic mass? 10.8, which is closest to what whole number? 11. So if its mass is pretty close to 11, that means 5 of those 11 came from the protons, and the other 6 have to be neutrons. Is it possible for me to find some boron out there that has only 5 neutrons? Sure. That's why that's not a perfect 11. So that's saying like sometimes we'll have just 5 and 5, giving us a mass of 10. But on average, we're closer to 11. In most cases, boron is going to have 6 neutrons, making it almost 11 in weight. Okay? Those ones were too easy. What about sodium? Let's look at sodium. So sodium, how many protons do I got? 11. Can I have 12? Because that's what? Magnesium. Can I have 10? Nope, because that's what? Neon. Okay. So how many electrons do I have if it's neutral? 11 electrons. Okay, and neutrons? Yeah, where'd we get 12? This guy is closest to 23. If 11 of that weight is from the protons, 23 minus 11 gives me 12. That's what my neutrons have to weigh. Is that part okay? No brains bent on that? Don't just tune out. I know the temptation, you guys. You're like, hey, this is boring. Me, I'm never going to need to know it again. See, I hated it the first 5 times. It was crammed into my brain. Screw it. I'm out. Do that. Okay? Modules 2 and 3 in this class are always the lowest scores because students see this stuff and they're like, I hate it. I just won't learn it. I'm going to get on my phone. Okay? Just tune in an hour and we're going to. Yes, please. I mean, you don't necessarily need to round ever, but the idea is if this is pretty close to 23, then we would say on average we most likely have 12. We wouldn't give you something that's like kind of right in the middle. I don't even know if there is one. Something like copper where you're like, plus the number is big, and we'll keep it pretty simple. So more than likely you're going to get something like phosphorus, and it's like 15 protons. This rounds to like 31. 15 protons, 16 neutrons. And we'll keep it pretty simple. So, but yeah, this is just an average weight. Back then, they'll come. Yeah, good question, you guys. So some of these dudes down here are in parentheses, like Rutherfordium and Dunerbernerbium and Scurbulurbium and whatever. These are like super unstable. Some of them are like we don't like theoretical, so they don't like exist in a situation where we can watch them and weigh them and whatnot. Very reactive. Those neutrons are just flying all over the place. Yeah, and we'll talk a little bit about some of these guys. Think of like plutonium. Where's plutonium on here? It's one of those things that we use for like reactions and explosions because it's just not stable. So that's why we can't really weigh it because how would you? They don't ever sit still long enough. That's like my weighing Weber State students. And you got a guy that's just running around. I'm like, come on, please get on the scale. And they like step on it and run off. And yeah, you're never going to be able to weigh that, dude. So, good question. So like with barium, if it's 137.33, how old would be giving us that? No, that's just evil. Where are we at? Like here? Oh, no, it's too much math. Yeah, and that's actually a good point. Realistically, you guys, it's like that little group and like this little group, a couple of these guys in there, those are the only ones that we see in the human body. So we really don't care about almost all of this stuff. Okay, if you've got these other things in your body, something's gone terribly wrong, right? You're like, doctor, I think I have krypton poisoning. I would have been drinking a lava lamp? Like, what the world's going on? Okay, so there's not krypton lava lamps. I have no idea. But the point is, in the human body, we just don't have that many things. Because this is anatomy and physiology, we focus on those elements that we find in the body. So don't stress about those weird ones. Now, if you swallowed your wedding ring, you might have some gold in there. But again, we're not going to. Or if you have mercury poisoning, possible, but not something we would expect to see naturally occurring. Yeah. Mm-hmm. Yeah, so if we're talking about positive and negative, it'd be like if I have 3 positives and 3 negatives. Those charges cancel out. For every positive, if you have a negative, then those just kind of go away. So we would say that they wouldn't contribute to the charge as long as they are balanced. So if I have a situation where there's 4 positives, but only 3 negatives, these guys will cancel out, and what I'm left with is just a positive charge. Or we can go the other way and say, hey, I've got 4 positives and 5 negatives. Well, these guys balance, these guys balance, these guys balance. I'm left with just a negative charge. So when we look at an element like carbon, for example, that atomic number tells us that it has 6 protons. And those guys are positively charged. If that element is neutral and everything is balanced, then we need what? We would have to have 6 electrons as well, so that the positives and the negatives are balanced and don't have a charge. If I took an electron away, and sometimes it helps to visualize. It's 1, 2, 3, 4, 5, 6 positives. If I took an electron out of here and we only had 5 electrons, now I've got 5 electrons. So those guys bounce each other, those guys bounce each other, those guys, those guys, those guys, and now I'm left with a positive charge. So it's a really good question. When you take one away, we're getting to that in just a second. So some of these elements, the way that they react, they will give away an electron because they don't like it, or they will gain an electron, and that'll start to mess with the charge. No, when we say neutral, the protons will always have a charge. You can't change that. It's just balanced with the negative guys. So if I have 6 protons in a neutral element, I would also have 6 electrons. So for every plus, I have a minus to go with it. And so there'd be no charge. I like these questions, you guys, because these are the types of things that you're like, I'm maybe too embarrassed to ask this. But there's another 20 of you who are like, yeah, I had that same question. I wasn't getting that. So let's take it slow enough that you're like, yeah, this is clicking. This makes sense. Please. Awesome. Did you guys hear that? And say it again. If you're adding or subtracting protons, really what you're doing is you're changing the element. So if I take oxygen and I take away 2 of its protons, it's not oxygen anymore. I just change that guy into carbon because carbon's the one that has 6 protons. But if I change the number of electrons, what I'm changing is the charge of that guy. Beautiful. Is there a time when I would do what? I can't take both because remember, if I take protons, I've changed the element completely. So I'm just talking about a different element. But I can remove electrons or I can add electrons. And we'll talk about when that happens in just a moment. Has a lot to do with where on the periodic table those elements sit. So here and then coming back. It's a good question, and it came up before. So we were talking about iron there. So I said, hey, you have iron. I just wrote it out, but you should in your heads automatically think iron. That's Fe. And I said we removed, what did we say we removed? Yes. So I said we removed 2 electrons. So iron by itself, if we don't say that it's an ion and we don't have a charge there, then you can assume there's balance between protons and electrons. If we're looking at iron specifically, it has 26 protons. If it's neutral, then it has to have how many electrons? 26. So then the question said we took 2 of those guys away. So if I only have 24 now, what's going to be my imbalance? Is it in favor of negatively charged electrons or in favor of positively charged protons? The positive guys. Because I have 2 more protons than I have electrons. And so I would be skewed in favor of being more positive. Does that make sense? Yeah, and it's tricky because I don't necessarily have to give you the number of those guys. If I'm just saying, hey, this guy started off neutral, and then we took away 2 electrons, and I want you to think, oh, now I have less electrons, more protons. I've got to be more positive. Good. These are good, you guys. These are like, hey, I'm grinding gears. I want this to make sense. They could be negative. Yeah, so how would I get a negative element? In fact, chlorine, when we talk about chlorine, in most cases, I just instantly write it like that. That's just like habit. Same thing with like hydrogen, same thing with sodium. They kind of come with a charge. They're not always charged. Those are ions. But why would chlorine end up negative? Yeah, so this would be a case where it's got 17 protons. It's always going to have 17 protons. I can't change that. But it picks up an electron. So now my imbalance is in favor of those electrons. It's going to be a little bit more negative. What would happen if it picked up 2 and had 19 electrons? Then it's going to have what? Like a negative 2 charge. Okay? This is good. Let's grind this out so that when we get to ions, you're like, oh yeah, that's just kind of what we were talking about. So here, and then we'll come back. And that's coming up too. Yeah, so we'll talk about something here. Here's sodium with its positive charge, and here's chlorine with its negative charge. And it's like, right? We'll talk about that in a second. But that's exactly what's going on here. As these charges change, their chemical properties or the way they interact with each other changes. That's why we say it's the electrons that determine chemical properties. Awesome. You're getting this. Mm-hmm. Kind of. So the question is, if we said, hey, we've got this iron that has a positive 2 charge, can I figure out how many protons this guy has? For sure. How do I find that out? It's written right there. That's an atomic number. Can I change that? No, because that's going to change the element. So really the only thing that would change or be different than 26 to give me that positive charge would be what? Number of electrons. Why would it not be a change in the number of neutrons? They're not charged. We don't care about them when it comes to charge. So if I'm plus 2, what does that mean for number of electrons? I have 2 less than I had at neutral state. Neutral means they're balanced, 26 and 26. But if I'm plus 2, that means I had to have lost 2 electrons. I can't gain 2 protons. That changes the element. So for mess with charge, the only thing that's changed is number of electrons. Can I swear? Or no? Try not to. Hell no. Please don't memorize atomic numbers. I don't know them. You could walk up to me on the street and be like, what's magnesium? I'm like, I don't know. Purple? Right? Yeah, don't memorize these. If we ask you questions, that's actually a really good question. If we give you a question about these, we'll give you the little square and all of its information. Okay, we went in here and we photoshopped out oxygen, and we'll give you that square and be like, according to this square of the periodic table, how many protons does oxygen have? Or we could be so evil as to say, how many neutrons does it have? And again, that's coming from the weight. Or we could say, if oxygen is neutrally charged, how many electrons would it have? Okay? Good question. Loved it. No. So I don't like a whole lot of memorization. we would give you like something like this and have you interpret it, but we're not going to be like, hey, tell us all you know about iron. You're like, well, I know that this symbol is Fe, but that's it. No, so we'll give you the information that you need to interpret it. Yeah. If you want to take a chemistry class and memorize all this, go for it. But I'm going to guess you're in this department or this college because you don't do that. So let's not. Good, you guys. I like that. Some of you are probably like, this is so boring. Great. I'm glad that you've got these concepts under control. I guess most of you are like, oh, good. This is good practice. I'm understanding this better. So I like the questions. And we got time. So, okay, so this is something more typical to what you might get on like a test. And then we'll ask you, hey, tell me about carbon. How many protons does it have? Electrons, neutrons, etc. Okay, so again, if we give you the mass number, sometimes we'll write elements like this. This would be the atomic number. Mass number is just your protons plus your neutrons. Because remember, the electrons don't contribute to weight. So if we're talking about the weight of something, it's just the protons and the neutrons. Okay, here are some guys we use in medicine. So look at this. Here's calcium. Its atomic number is 20. So why would I have a mass number of 47? What have I got? 20 protons and 27 neutrons. A little bit imbalanced as far as numbers go. Look at this radioactive iodine. Its atomic number is 53. So I have 53 protons. Its mass number is 131. I have 78 neutrons. That's a little bit funky. This isn't something that we just see floating around, hopefully not, in the environment. Because what would you guess those extra neutrons are going to do? Just get out. Pew, pew, pew. What would you guess these neutrons are going to do as they go flying away from this thing? In fact, I'll tell you, we do this in medicine. So someone's coming to the doctor and they've got a big old goiter. You guys seen goiters? It's like a big old huge neck swelling thing. I'll show you a picture. First time I saw a goiter in real life, I was like, goo! What's that? Like, that's cool. That's okay. Right? So be ready for it the first time. You're like, holy, what? Whoa! Okay? A goiter. Sometimes we call it a toxic goiter. It's when your thyroid gets big and scary and inflamed. So sometimes we'll get the thyroid that's growing new tissue. It could be cancerous. It could be just other types of growth. But we don't want it. So iodine is an element that the thyroid uses to make thyroid hormone. It's the only organ in the body that likes iodine. So we can take this radioactive iodine and we say, eat this. And you're like, for reals? You want me to eat radioactive iodine? We're like, do it. So you eat it, travels through your body, gets in the blood, and it starts to collect in your thyroid. It doesn't collect anywhere else, because nowhere else cares. But what would you guess those neutrons flying away are going to do? Well, blow up little pieces of your thyroid. But if your thyroid's all big and scary and growing new tissue anyway, that's what we're trying to do. So we can do a thyroid ablation, blast parts of it away using radioactive iodine. Cool. So the element itself, we get this guy from nuclear reactions, but it's unstable, and then we can use it. Okay, these other guys we can zap them through your body. And they go right through you, and we can use them to take pictures without having to open you up. Okay. So that's the idea. So in medicine, some of these imbalanced electrons are very, very useful to us. Okay? In this one here? So we would have to look at a periodic table and know that its atomic number is 20. It's always 20. Yeah, so its mass number would be 47. So I know 20 of that weight has to come from the protons. And the only other thing contributing to weight would be the neutrons. Does that make sense? So if it's calcium, it's got 20 protons every time. I can't change that. If its total weight is 47, then I've got 40. Oh, that's not going to help. 47 is its total weight minus the 20 weight that's coming from the protons gives me 27. Where's that other weight coming from? The only thing it could be is the neutrons. Yeah, if we're going to get real crazy like one of these, we would say like, hey, I've got radioactive iodine. Iodine has an atomic number of 53. But if its mass number is 131, what's that saying? That's just saying we got a whole bunch of extra neutrons. That make sense? Yeah.
What can you figure out about the electrons?
Say it again.
Like how do you know? You just assume that it's neutral?
Yeah, so good question. How would I know about the electrons? Yeah, so chlorine would typically carry like a negative charge. Calcium in a lot of cases wants to be positive. But if it's written like this and there's no other information, assume it's neutral. If I wanted to say it was positive, we usually put a little plus sign right there next to it. I can put 2 plus signs if I want to. Hey, calcium's got a +2 charge here. Or I could put like a little negative sign, depending on what it is. But if you don't have any information about charge, assume it's neutral. Good. Weight is what? Protons and neutrons. Yep, just that. So atomic number and atomic mass. Atomic number is just protons. Atomic mass is protons plus neutrons. This would be the same as what we would see on the periodic table for the mass. But in these cases, we've manipulated these guys to be weird. Can't, not for electrons. So atomic mass tells us what? How much it weighs, which is what? Protons plus neutrons. The way we get the charge is how many protons we had, and then is it neutral? Well, then I have to have that same number of electrons. And we're going to get to electrons in a second. Let's play with that and see if that doesn't clear that up a little bit. Okay, yeah, these guys, these are weird. So when we see something written like this, what we're talking about is, hey, we've messed with this element to make it useful to us. Okay, here's the hydrogen thing, that idea about the mass. 1 out of 100 has a neutron. And that's why the average mass isn't a perfect 1.0. This is a visual way of looking at what we were just talking about. So once again, something like nitrogen, if I look at its atomic number, it's 7. What does that mean? 7 protons in my nucleus. If it is neutrally charged, what does that mean for electrons? 7. 1, 2, 3, 4, 5, 6, 7. Okay, that's all we're saying. It's just a visual way of looking at it. You'll notice from this picture that we organize these electrons into shells. And that's going to play out in just a second, too. So hydrogen, 1 proton, 1 electron. Okay. As we look at these other ones, here's carbon, 6 protons, and then 1, 2, 3, 4, 5, 6 electrons, because it's neutral. Look at iodine. Oh, forget it. Okay, but you can see, hey, if I got 53 protons, I'm going to assume there's 53 electrons there, because it's neutral. Perfect. You know it's neutral because there's no positive or negative written next to that symbol. Okay, so let's go off of that. What if I had sodium, and when I wrote sodium for you, I wrote it like this. Sodium, beep, beep. What would that mean? That this guy has an extra or 1 less electron? 1 less. It would be missing 1. Look which one I blasted. The only guy in that outer shell. And we're going to talk about that in a second. But it would make sense. If you're going to get rid of one, that's the guy to get rid of. Okay, look at, do we have chlorine in here? Look at chlorine. Usually chlorine is negative. So what does that mean? It has an extra electron. Where am I going to add it? 1, 2, 3, 4, 5, 6, 7. Empty. That other shell, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's that 8th electron. 8's kind of a magic number we're going to talk about in a second. Yes. Did you guys hear that? That's exactly right. If it's a positively charged ion, we haven't even really defined ion. We're getting ahead of ourselves, but that's totally right. If this sucker is positively charged, then I took away an electron. If that guy is negatively charged, then I added an electron. Remember, I can only mess with electrons if I'm messing with charge. Can't mess with protons or I'm changing the thing. I'm adding or subtracting electrons. That's exactly right. Yeah, good question. Why do we have mass numbers being these guys?
Why not 39, 40, or 141?
Because this is just how it naturally occurs in the environment. So sometimes I'll have 19 protons. I always have 19 protons, but sometimes I'll have 20 neutrons. That's what gives me that mass number of 39. But sometimes I have 21, and sometimes it just has 22. Because those are forms that exist in nature and we see them. So we just take like, hey, what's out there? Let's weigh it and get the average weight. So in some situations, it's picked up a couple extra neutrons. Some situations, it doesn't have as many. Just the way the world works. So yeah, that's a great question. Okay, don't think too hard about some of this stuff, or you're going to start getting like all theoretical and you're just going to mess with your own brain. So let's look at this electron shell thing for a second. Okay, this is another one of those concepts that can be kind of tricky if you overthink it. I'm going to give you a simplified version. In fact, this simplified version, you may be like, this isn't how I learned it in chemistry. Fine. That doesn't hurt my feelings. Keep it simple for what we're doing. Okay, so here's the idea. The innermost shells, if I've got electrons all the way out, you don't touch the inside stuff. Okay, that's not going anywhere. It's almost like a person in the circle of friends, right? You got your besties right close to you. You're not taking away the besties, but now you've got like your fringe friends, you know, that you don't really care about. You kind of hang out with only sometimes. If one of those people's like, I'm out of here, you're like, yeah, screw you, I didn't know you anyway. Okay? But the inner guys, you don't touch them. Okay? So those electrons that are outside or only loosely, this is your nucleus, this is you, those guys can kind of come and go a little bit more easily. Okay, you go out with a big group of friends, you're like, who's that person? Who cares? Right? Your besties are there. That's okay. And those other ones, you're like, if they were there or not, I'm not really going to care. Okay, that's the idea. So the outer shell of an element, we call it the valence shell. It's just a way of saying, hey, those are the electrons that can come and go, and we're not really worried too much about that. Okay, I can't touch the inner ones, but it's the outer shells. So, look at oxygen here. Here's the nucleus with its protons and neutrons. That first shell, its magic number is 2. Okay, that's where it wants to be stable. That's where life is good. So it has 2 electrons in that first shell. You're not touching those because it's happy, it's content, it wants to be that way. This outer shell then, it's got 1, 2, 3, 4, 5, 6. 6 electrons in the outer shell. Okay, the magic number for the second shell is 8. Okay. Magic number for the third shell, for what we're going to be doing, is also 8. Okay. Oh, I learned it could be 16 or 32. Okay. For me, for our purposes, keep it simple. Okay. And the reason we keep it simple, or what we're getting at, is we're trying to be like these guys, is the idea. Okay, remember that we said the noble gases were what? Snotty. Remember how I said that? They don't share. They don't play with other people. They're just fine doing their own thing and don't want to interact with anyone else. That's what we mean by snotty. But what we meant by that, what I was saying, is that their electron shell arrangement is the way that other elements want to be in order to be perfectly content and happy. In other words, let's look at helium. Helium, and you can't see it, it's kind of blacked out, has an atomic number of 2, which means it has 2 protons. That's a given, that doesn't change. Let's say that the weight being 4 here is it has 2 neutrons. And if it's neutral, how many electrons is it going to have? 2 electrons. So if you're to draw this guy, here's the nucleus, 2 protons, 2 neutrons, and here's its outer shell, or its only shell of electrons. It's got 2, First shell, 2. What do we say the magic number was? 2. Is neon going to give up an electron or accept an electron? No, it'd be all out of whack and out of balance. 2 is where it wants to be. That's why neon doesn't ever combine or play with anybody else. Now you're going to find, like, I've got this element, calcium neon, that I'm doing something with. Neon doesn't mix with anybody because it's snotty. It's a noble gas. Okay, let's look at neon. Okay, sorry. Helium, I just said neon. I shouldn't have said that. Helium was the one that we were just talking about. It's noble, too. Neon, it's got 10 protons, 10 electrons. So how would they be arranged? Here's my nucleus. First shell is going to have what? 2. Second shell is going to have what? 8. And I like to put them in pairs here. 4, 6, 8. Would it give up an electron or get rid of one ever? Give up or accept one, sorry? No, because 8's the magic number. This is where it wants to be. So neon is never going to play with anybody else, just like helium, because it's content. Okay? It has 10. So if we look at it, its atomic number is 20, so it would have 10. 10 protons, 10 neutrons. Okay, last one we'll look at, and then we're going to play with these other ones, and I hope that it'll click. Look at argon, another noble gas. It has 18 protons. So if it's neutral, it's going to have 18 electrons. Its shells, here's my nucleus again. Nucleus. First shell, how many electrons? 2. Always 2. Second shell, 8. Always 8 in my second shell. So that gives me a total of how many electrons? 10. So in its outer shell here, 8 again. And that's happy. That's the magic number. So all of our elements that are in those same rows on my periodic table want to be like those snotty noble gases. That's where we would want to be. So this is like the gold standard for stable elements. So let's look at it. Let's see if we can't make sense of this. Here is neon. Once again, if we look at neon, so neon, there's your nucleus. It's got 2 electrons in the first shell, and how many in the next one? 8. So if we were to take its little neighbor here, fluorine. Fluorine has an atomic number of 9. Always 9 protons. But if this guy's neutral, it's going to have what? 9 electrons. So fluorine, there's its nucleus. How many of those electrons would be in the first shell? 2. How many are going to be in the next shell? 7. Because I only have 9 total, right? 4, 6, 7. So what would you guess fluorine is most likely going to want to do? Get an electron. Okay? If I get an electron, now who am I like? Neon. I've got 8 electrons in the outer shell. And that's my most happy, stable state. So in most cases, when we're looking at fluorine, what would you say it's going to be as far as the charge goes? It's going to have a little negative. We call it fluoride. Where do you see fluoride? Toothpaste, that crap I had to drink as a kid in elementary school, blah. It's something that we see in things, fluoride, because it comes together with other things. Okay, the easiest way for fluorine to get to a stable shell pattern was to pick up an electron. Let's look at chlorine. If it picks up an electron, it's now got more negative electrons than it had positive protons, so it would be more negative.
So when you write it as negative, then that means it has the outer shell is 8?
Yes, in fluorine's case. So if I write it with an F and a negative, that means I've picked up an electron. So in that case, I would have 10 total electrons, 2 in my first shell, 8 in the second. Let's look at chlorine. See chlorine more often. Here's chlorine. I'm not going to draw the shells for you, but if it has 17 protons, what's it got for electrons? 17. Always assume that it's neutral here. So How many of those electrons are going to be in my first shell? 2. How many of those electrons are going to be in my second shell? 8. How many in my third shell? 7. Because 2 plus 8 is 10, plus 7 is 17. So what would you guess chlorine is going to want to do in order to get to that happy place like the noble gas? Add an electron, because now I've got 8 in my outer shell, and I'm good, just like argon. So in most cases, if chlorine ionizes or changes the charge, what do we end up with? Bleep. Chlorine with a negative. Is that making sense? Okay, let's play with sodium for a second. Chlorine study. Sodium has an atomic number of 11. 11 protons, 11 electrons. What are the shells going to look like? First shell, 2. Second shell, 8. Third shell, 1. Why wouldn't I just pick up 7 electrons and have 8 in my third shell and be happy? It's easier just to nuke that guy. Just get rid of one. So in most cases with sodium, when it ionizes, it just drops an electron. So if I now have one less electron, what's going to be my charge? Positive 1. Okay? Nope. If I'm writing this, the charge says, hey, I've got an imbalance in protons and electrons. And if electrons is the only thing I can really change, then this guy says you've lost an electron. This by itself is neutral, balanced, normal sodium. This is now sodium that has given up one of its electrons. A little bit more positive than negative. Nope. If we're talking this guy with no charge, the balance is protons and electrons, not shells and where the electrons are. Neutral just means I've got same number of protons, same number of electrons. This guy that we look at, it's got happy shells, and that's the balance we would be talking about there. Its shells are where, or it has electrons in the shells as it would want to have them to be like these guys over here. So if I add that symbol on any of them, I'm just talking about the balance of electrons. And I've got more or less. So with a little plus sign, I've got less electrons than normal. If it's a negative sign, I've got more. So let's look at it, going back. So there's my electron shells. This is what we were talking about. So they want to be like the noble gases. This is just another way of looking at filling those shells. So let me skip ahead. I'm going to come back to that isotope thing in a second. Because we got ions over here. So here are the ions. This is exactly what we're talking about, where I have a deficit or an excess number of electrons. Okay? So, sorry, deficit or excess number of electrons. That's all we're saying. So an ion is something that carries a charge. It might have a negative charge, which would mean what as far as electrons go? I've got more electrons than protons. If it has a positive charge, what? There's more protons than electrons. So the positively charged guys we call cations. Okay, write it like this. Cation. It's got a big positive charge right in the middle of it. Okay? Or if you like cats, they're positive. You're like, I'm a cat person. Yay. Okay, yeah, cation, positive. Anion, these guys are the negative ones. So I think of like anion, negative, negative. Okay, that's why it's got N's in there. Screw the N in cation, that doesn't help. But the extra N's say negative. Okay, or an kind of looks like ant. Wants ants in their house. Cats? Cool, great. I'm cool with that. That's positive. Ants in my house? No way. No thanks. Whatever it takes, don't forget cations are positive, anions are negative. And that just comes down to the balance of electrons. Okay, so here's sodium. If you look at it, it's positively charged. So it has done what with electrons? Dumped one, right? Potassium is positively charged. What has it done? Dumped an electron. Chlorine is negatively charged. It's done what? Added an electron. Bicarbonate, it's negative, it's added an electron. These are probably the guys you're going to see most often. When we put them in solution, like in a fluid, we go from calling them ions to calling them electrolytes. Okay, and where have you heard the term electrolytes all over the place? Gatorade, right? Gatorade became popular. So people at the University of Florida, as their athletes were working out, they said, you know what, these guys are sweating a lot. And sweat isn't pure water. What else do you sweat? If you don't believe that, find the next sweaty person you see and lick them. And you're like, Dr. Price is right, you're salty. They're going to be like, who are you? Weird, right? But the idea is University of Florida people, they're like, you're losing water and sodium and chloride, the salty stuff. So what about instead of just drinking water, we drink water with some of that salt in it? Gatorade. I love this commercial.
Dombrowski picks up speed and breaks away. Gatorade is first aid. Here's Evans showing some hustle against.
Look at those shorts.
When you exercise,
Woo!
potassium, fluids, minerals, Gatorade Thirst Quencher helps put them back fast.
That's why the pros drink it. It's Thirst Aid.
Gatorade is first aid for the deep down body.
And the crowd goes.
Yeah, baby. Okay, awesome sauce, right? But the very earliest commercials, they're trying to teach people, hey, you need some of these electrolytes back in your system if you're sweating because you're out playing with your kids. My dad had played basketball in shorts that short with us. Would have scarred me for life, right? But the idea is, yeah, we return some of those electrolytes, those positively charged or negatively charged ions that we see in the body. You lose them through sweat, bring them back in through Gatorade or Powerade or whatever it is. Okay, we okay on the idea of ions and electrolytes? Okay, let's zip back through this part. This part's easy. So this idea of an isotope. We've already talked about isotopes. Iso means same. So these are same element, different weight. Ions, you could say, are the same element, different what? Charge. Great, because we're changing electrons. So the same element, but a different weight. What am I changing? Protons? Nope, because that's going to give me what? New element. So the only thing I can be changing is neutrons. And that's just what we were talking about a second ago with the radioactive stuff. So we've already talked about this. So sometimes I have hydrogen, and in most cases, it's a proton. My little blue cloud here is showing me the electron. Great. In some cases, I can end up with this guy called deuterium. It's just hydrogen that has a neutron. So if this guy only has one proton, 0 neutrons, then it would weigh what? 1. This guy's picked up a neutron, so it's going to weigh what? 2. Look at this funky thing. It's got 2 neutrons. So this guy's going to weigh what? 3. Okay? These guys are weird. They're not normal. This is normal. Okay, so in most situations, our hydrogen just has a weight of 1. Great. Every now and then in the environment, we find this guy, this deuterium. Freaky. This guy, tritium, hydrogen with 3 weight or 2 neutrons, weird city. We have to make this in like a lab with nerds in coats doing something. Okay? You can actually buy tritium keychains. Guess what they do? They glow. They're like, here, get this keychain. Put it in your pocket, right by your testicles, and carry it around your whole life, right? It's not high energy. It's not like you're zapping yourself. But the exit signs, most of the time, those guys have tritium in them. That's what helps them to glow. Okay? Because these molecules, now we've packed in extra neutrons, aren't very stable. They give off energy. Okay? That's the idea behind a radioactive isotope. So this just goes back to this atomic weight that we've been playing with already. Why would iron have an average weight of this? Well, in most situations, it's going to have a mass of 56. So I have a disproportionate amount of protons and neutrons. 26 protons, 30 electrons. Whoop, neutrons, sorry. Just got done talking about electrons. That's why that guy would weigh 56. But every now and then, like 2% of the time, iron weighs 57. And 0.3% of the time, we find it weighing 58. And 6% always. So we just take the average, and that's where that atomic mass is from. Okay, again, we've already kind of talked about this, so don't think this is new. Okay, there's your types of hydrogen. I would recommend you know these names. Wink, wink. Okay, tritium is a hydrogen molecule with 2 neutrons. Deuterium is a hydrogen molecule with 1 neutron. And regular old hydrogen doesn't typically have a neutron. So back to that idea where we were blasting someone's thyroid with this unstable molecule. When they are unstable, we call them radioisotopes. Okay? We showed you some that were important in medicine. But the idea is they don't like to just stay where they're at, and they release those neutrons, and with that release we get some energy. Okay, that's where we get this nuclear fission idea. So here's uranium-235, pretty unstable molecule. So we get a reactor, we put some of this uranium in it, and then we flick. It's like a person with a booger. We flick a neutron at it. That neutron hits its nucleus, and it kind of irritates it. It pisses it off. It makes it even more unstable to where it splits. So the splitting of a nucleus is nuclear fission. But now I just split this guy, and I ended up with 3 random neutrons just flying around. Well, what would you guess this neutron's going to go and hit? Another uranium-235. And what's it going to do to that? Split it. Get 3 more neutrons, and what are they going to go do? Each one of those is going to go split another one of these atoms here. So if I have a whole lot of these atoms, and I just started splitting them, and every time I split it, I got 3 more neutrons to split other ones, now what's happening? A nuclear reaction. Okay, this is what nuclear power plants do. This is what nuclear or atomic weapons do. We get a whole bunch of this or another one. We put it in a bomb. As soon as that bomb hits, we start this reaction, and it just spreads. Okay? That's what happened in Hiroshima and Nagasaki. Super sad deal. Because we're like, hey, Japan, surrender. They're like, no. We're like, hey, surrender. No, we're like, well, we've got this new thing. Let's try it out. And then we kill hundreds of thousands of people. Not a good thing, right? Thank goodness it's never happened again. But ugly mark on the United States that we're the only people on the planet who have nuked somebody else. But fortunately, the planet has learned, hey, we can't mess with this anymore. This isn't something that's okay. Because when you hear weapons of mass destruction, all that, we're trying to make sure that we don't ever unleash this kind of power on other people. But unfortunately, we do see these radioactive isotopes just in nature. And sometimes it's fallout from nuclear testing, nuclear power plants, nuclear bombs going off, whatever it is. So we talked about iodine-131 already. We use that to destroy thyroid tissue. We'll get to that down the road. But, and I love this picture, sometimes we get some of those byproducts of these nuclear reactions. So we call it fallout. So it rains, and some of that fallout goes into the ground, and then a caribou eats it. And then you, because you're an Eskimo, kill the caribou and eat it. And I love that we have arrows. I think of this. And then the wolf eats you, right? Now the wolves, these molecules, these unstable guys that we're left with after chemical or nuclear reactions, they can end up in the environment for long periods of time. Okay? And they can cause long-term damage and effects. So that's the problem. We don't want fallout from nuclear reactions getting into our system, because now what would radioactive guys do once they're inside your body? Start flying around breaking things in your cells, and that's bad news. Okay, iodine specifically, yeah, sure, that's just thyroid, but other radioactive isotopes can hurt other types or other parts of the body. So certain types of cancers have been directly linked back to exposure to radioactive material. So we don't want it. So Chernobyl, this was a guy in Ukraine that it was a power plant that the nuclear core basically like exploded and all of this nuclear waste started getting released. They told the town, evacuate now. Not like go gather your stuff because this radiation's coming. If you don't get out now, you're going to get it. So you can tour Chernobyl. I've been to Kiev a couple times. You can go through the city and it's like there are entire tables where there's like plates and forks and cups out and it looks like literally people just vanished because they did. Because word came out, sirens came on, they're like, hey, you live right by a reactor. If you don't get out now, you're going to be nuked, literally. And so people just, the town abandoned it completely and couldn't go back because there was all that extra radioactive material. So they just had to leave and start brand new fresh. So just with time. Yeah, so question, how to get rid of it? We call it a half-life. So we can see how long does it take for that unstable molecule to break apart to where it's now no longer unstable. So some things like the iodine, it's like a week, and that guy's back to normal. But some of these guys, as we get stronger, like plutonium that we use, it's thousands of years before those things are back to being okay to be around. Okay. So now I don't know exactly the half-life in Chernobyl, but people don't live there anymore still because we're worried about the fallout still being in that area. Yeah? Just know what the idea is, that this is like how long it takes for that thing to get back to being stable or to completely decay is what we say. All right. So you are exposed to some radiation. You may have been exposed to some x-rays. It always creeped me out. Remember going to the dentist as a kid? And it's a lot better now, but I remember sitting there in the chair. They make you wear the lead shield, the little thing on your face, and then they would run and hide. And I noticed that as a kid. I'm like, wait a minute. Why are you hiding? As you're like, like, well, yeah, that person would be exposed multiple times every single day versus you getting your x-rays once or twice a year. Not as big of a deal. But that x-ray tech's not like, hey, I'm just going to stand right here. Zap, zap, zap. Yeah, not so much. Okay. So this is not something you have to memorize, but if you look at this, when we look at that iodine building up in someone's body, we see certain areas of the country that have more of it than other areas. Why would you guess? Nuclear testing. This is fallout. So we're seeing these products still in the soil, still in the environment, and people being exposed to it a little bit. So take-home message, don't go to Montana, North or South Dakota. Ever. No. It's not the case, but we see higher levels of these guys just because of nuclear reactions taking place in those areas, or nuclear testing. Your brain's full? This enough? Okay. We're going to stop with this idea. What this is here, what we were just about to talk about, we can manipulate these molecules to do stuff for us in medicine, but you got some studying to do. Please, I'm going to do another Kahoot next week, and if it goes the same, you'll be angry. I don't know what that means, but be angry. Thanks, you guys.